Welcome to my EGB 241 DC motor design. I'm Joseph Haddad and I will be presenting to you what I have proposed for this task. This presentation will look into the design I have tasked, and this design is aimed to perform best when it comes to torque. As you can see above, there's a front orthographic, a rear one, and a top view, which will be further explained in the coming slides, but this is what it looks like right now, just to show you an insight. In terms of constraints, of course the DC motor must be powered by DC. It can use a minimum of 5 coils and a maximum of 8, of which the design uses 8. It must self-start, so no little push to give it a start, it must start all by itself. It must use a maximum of 45 meters of copper wire, can only use 2 magnets, and it cannot exceed 30 volts and 5 amps. So calculations on both Excel and MATLAB were conducted. These simulations can be further scaled into the real world C for a scaled up design, but for now these calculations are used to measure the performance of how the design might perform if actually constructed. So the maximum rotational speed is around 2,950 RPM. It looks at max rotational speed at the maximum torque, which is 1,750 RPM. Checks it in radians per second. Looks at the maximum generated torque, which is around 0.03 Newton meters. This is the maximum power it can produce, but in reality it might actually only produce that much. This is the input power that will be put into the motor, and the efficiency is down here at 11.89%. The calculations from Excel will then be put into MATLAB as shown here in the graphs. And these graphs give the insight to how the motor will perform in the real world against time. As you can see, the speed, back EMF, current, torque, and angular acceleration have all been plotted against time to see how the motor might actually perform. A maximum speed here is reached of 2,100 RPM, and that takes around just under 2 seconds to reach. The back EMF is maximum of 2.5 volts, and that will take also around 1.5 seconds to reach. The current versus time, it starts off at 3.5 amps, but as it reaches around 1.5 seconds, just like speed and back EMF, it reaches the minimum torque which is required to keep the motor running, which is around 1 amp. The torque versus time is an interesting graph. It looks at all the magnets. So in the green is the one that's been selected, so the 3495 series magnet, which is a bit hard to see, but it is performs just a bit better than the 3470 magnet, which is in blue. But the green one's just a bit better. So that's the one that's been selected for the design, as it provides the maximum amount of torque. The angular acceleration has been calculated here, so that over time, the same as the speed, back EMF, current, and torque. It starts off at accelerating, and then once it reaches max speed around 1.5 seconds, which is 2,100 RPM, it stops accelerating in a high rate because it's now at a constant speed. Then here, the speed versus an increasing torque has been measured to show that as the torque increases, yes, in fact, the speed will decrease down to 0, which is at 0.04 Newton meters, which is here shown in the torque versus time graph, which is 0.04. So the applications of this design, as mentioned before, the calculations can be scaled up to measure how a motor such as these real-world industry motors can perform. This small-scale design will provide like an insight of how it could perform if it's scaled up. Any small adjustments can be made, all at a smaller scale, to make sure no big financial mistakes or a lot of time will be wasted, because at a small scale it is easy to just switch and change parts and it won't cost a lot. As the next slide goes over the pricing, as you can see, it only costs around $69.40 to make the entire design, which is a lot cheaper than having to actually build the full design, as mentioned before. The costs here of these materials are average costs taken from visiting different sites, eBay, and many different suppliers that could supply these parts. And an average has been taken to show a sort of market representation of what you could find. This price isn't 100% accurate. It is a rough estimation, and it could be a little bit more or less, but it's there to provide a rough insight. The back iron could be added, which will provide a better, less flux leakage, which is recommended, but it's an optional choice. Now I'll discuss the motor size and structure. As I showed you before, this is the top view of the design. It shows you the design is 13 by 13, and the height is also 13 centimeters. This provides a square design which is easy to construct and will mean a very stable construction if it's all the same size and perfectly designed. There's a shaft here with the armature and the commutator present on it, and the magnets are on the left and right side, which is a 3495 series. And the air gap here can be adjusted depending from testing how well it performs, how much vibration there is. Here's a 3D model, which is 13 centimeters high as mentioned above. This makes it a square design with the shaft here and the bearing at the front here and at the back here, allowing it to rotate when the commutator receives power. And this is how it might look like if you come to actually construct it in a 3D. In terms of approaching this design, it should be conducted in 3 steps: assembly, testing, and final design, and they should be done in that order. In the assembly stage, you should make sure that the construction of the frame is really rigid, and so it'll allow the magnet to be put as close as possible. And when it comes to the windings, they should be wound carefully so that the least amount of space is used, so all the wires can be fit in their slots. Then once the assembly is finished, testing should be conducted. Here, as mentioned before, you could move the magnets closer if you find that it tests to be good with vibration. But instead of just running at its full potential, you should test it slowly in small stages to make sure that it runs and actually works, and if there's any adjustments that needs to be made, you can do them before actually putting it at a full-scale test. And in the final design, you can stress test it, see how well it performs, and do all the final testing to see how it should perform and see if it actually performs as it should. In terms of a risk analysis, there are 6 main risks that I've identified. These are burning out the brushes, heat, vibration, spinning parts, and electricity. Burning out the brushes and heat pretty much come close together. As you can see in this image, if you overstress the motor, a lot of heat is generated, and this could potentially burn out the brushes. Heat is something you want to avoid touching, and you don't want to overstress the motor so that it burns up, as it could cause a risk. Vibration is also another risk, and it also falls straight in with spinning parts, because since the motor is constantly spinning and causing vibration, if it breaks due to vibration, parts could go flying and it could hurt you or impact you. So you gotta be careful, make sure everyone who's watching the design operate is far away from it, and safety glasses are used if you are nearby. And the last one's electricity. Of course, you have the ability to run this up to 30 volts, which if it's not needed, you should not run it at 30 volts, but it's always safer to ensure all wires are well insulated and away from your fingers or body. In terms of future development, a more extensive range of magnet types should be looked into to see how well it might perform under torque conditions with better magnets. Different winding types could be looked into, as we have only looked at lap winding for this design. However, you can look at wave winding or any other commonly industry used windings, see if it gives the improvement in the torque or not. Better construction materials such as like a welded steel frame could mean that the design will vibrate less and you can move the magnets even closer. And it could allow you to use curved magnets, which have the least amount of flux leakage to give the best performance. So in conclusion, we looked at the risks, we simulated the design, looked at a potential schematic, the financials, and the applications. And all that's left is to actually construct a design and see how it actually performs.